Okay, so to make a quick recap, the briefs asked for a big ring with an unconventional layout of stones, different from traditional pavé. So we came up with two ideas and started working on the right one. And we have made quite a progress so far by being able to create the curve by intersecting the outer surface with planes at regular intervals. But we want to be able to control a little bit more about that. So we're going to try to jump into Grasshopper and see if we can have more control and maybe make this design more flexible.
Okay, so just let me show for a second where we got during the first episode. We had the upper surface. I don't think we need the brief sketch anymore. So we had intersection curves, the ones that we got through intersection between planes and the surface. This is the spacing that we were looking for at alternating intervals. We placed planes that cut through on the upper part of the ring and generated this sort of like roundish curves. And finally, we placed the diamonds there. And what we want to control here is the spacing of the diamonds, maybe, and most of all,
the spacing of the sections.
And the spacing of the sections, exactly. And so
maybe the number of diamonds as well. I don't know.
Yeah, sure. And doing exactly. And so, another thing that it's interesting. Look at this. You see, the spacing is not the same towards the edge on one side and the other. And maybe this is something we want to, refine a little bit while we're doing this in Grasshopper. And the other advantage is going to be that if we just change the shape of the ring, the definition will adapt to the new changes. And so I think it makes it quite convenient to invest some time in doing this in Grasshopper.
I think we better start off fresh in Grasshopper. So we want to control how many planes are creating the intersections. And to do that, we need to extract the mid isoparm that is in red in this screen and divide it by some number that we want to control. And we can see an example of that shown by the points on such curve. So this surface is symmetric on both y-axis and x-axis. So we know that if we get the parameter 0.5, which is the middle parameter in a reparameterized surface, we get both mid isoparms. We can then split it in half and work a little bit more on it to get the divisions, and we'll see the rest of the definition as we go.
Okay, so let's start with Grasshopper. We have our surface. We want to get that surface in Grasshopper. And so one parameter, and we set one surface to this surface. So we have both the surface in Rhino and in Grasshopper. Now, there's one thing to say here. We will play with parameterization of the surface to extract the isocurves. So it's worth spending a few words on this. Now, if I select the Rhino surface, you will see that it's a valid surface. And for what concerns U and V, this is degree 3 with a certain number of control points. But the interesting thing is that domain. Difficult numbers to remember, like this is ranging from 18.5 something to another value, and this even has negative values. So these two domains are something that we want to remap to a one simple and conventional domain, which is 0 to 1. Now, this is something that you could do in Rhino directly, and there is a command for that, which is called a reparametrize. So this will pick the starting domain. You see, you can change it to something that you want. You can start with like 0, and we will do that in Grasshopper. Once the surface is in, you can right click, and for curves and surfaces, you have this reparameterize. It will be changed to 0 to 1, both in U and V directions.
Okay, so now we want to get our isoforms. So we can do that in the curve section, curve comment section. Under the spline menu, we have a component called isocurve, and this will provide the isoforms for a given parameter. We already talked about reparameterization. So the domain is now 0 to 1 in both U and V direction. So we are sure that the parameter 0.5 is in fact the middle isoform. So this is what we're going to do. All right, so now the tricky part is telling apart U and V, because we usually have no visual indication of which one is which. So maybe you can show something, some kind of trick.
Oh, yeah. Yeah. I have a method that I use a lot. And I have my personal flavor for the ghosted view, which has different colors for U and Vs. You see the blue visualization means that I've changed something. And you go into the surfaces and use specific colors for U and V. And so I use these two colors. This is a lot of help because it helps me understand when I'm doing surface on surface and all the commands that will take into account U and Vs, I know beforehand. Okay, so I know already that what we're looking for is going to be U curve.
So what we want to do is get that curve. So it would be U as the output. We want to divide it by some parameter, which is conveniently going to be 0.5 again, because we want just half the curve.
So this is the curve we want to shatter, which means divide, and T is the parameter. We already know that that's going to be 0.5. Now, for the sake of consistency for people watching the video, I will just panels all the times. I could just input the value over here, but just. So now we have a shattered curve, and we need to find which piece is going to be.
Let's go with the least item.
Planar curve, planar curve. This is the two pieces divided. And so which is which? I don't know. Index is going to be index 1. And now we're picking the right thing. Now, maybe something we want to control here is where we are starting. Where is the starting point and the end point? I can get the endpoints. Yes, this is showing start and end, but maybe adding a parameter point will tell us where the starting point is. So this is the starting point. So the direction of the curve is from here to here. Okay,
and that's what we want, isn't it?
Exactly. So this is just for, making things consistent. We want a division by distance, okay? So that we keep a constant distance between the divisions.
We also want to be able to control the number of points.
Exactly.
So this distance is going to be controlled by a slider.
Absolutely. So I don't think the initial number, the minimum number, should be, I don't think we need 3 decimal points. I think 1 is enough.
Yeah, I agree.
And the minimal division, sometimes maybe we will be using very small stones, so we can, nothing prevents from using small numbers. And so let's say we have a upper value like 5. We're never going to use 5, but yes. So there we go. We have small divisions and larger divisions. Now in Rhino, when we did this thing,
we went for 1.5.
1.5.
We want
yeah,
to be
exactly.
consistent, right?
Yeah, I'm just typing 1. I'm just using 1.6, but makes it makes no difference at all. Okay, so what's next? You see how nice and easy everything is? Absolutely. We're just repeating the modeling strategy that we use in Rhino, except we're doing that in Grasshopper. So we need then planes over
Yes,
here.
we need the planes.
X, Y
X, Y,
planes.
yes.
Yep. And we want the origin to be on the division points.
We can get our intersections already.
Absolutely. And it's going to be rep plane.
All right, so do we want to have a look at how those intersections look in the panel?
Oh yeah, it's going to be closed and open curves. Absolutely, we can see that. We have a number of closed planar curves, and then at some point we will have, you see?
Yes.
You see two curves because it's going to be one on one side and the list is showing the other one on the other side. This is right. What we get here. So maybe we could look at the length of the curves, because you know what, considering that we have to place stones all around, the length of that curve should not be smaller than something. Just think about the three stones like at the vertex, at the vertices of an equilateral triangle. That's the minimal layout for the stones. The size of a circle passing through the 3 points for 1.5 stones should be somewhere over 5. I'm just, just using very broad figures, but something like that. Let me just check the length of these curves. You see, we have a very small. So that would be perfect 0 if you were using, for example, as a division method, planes. The one thing we want to do here, we want to apply some sort of filter that will just kill any curve which is below. I'm saying 5, but that's something we could control.
Okay, so now we need to get rid of everything that is too small, and we want to decide what too small is. So we can test the length of those curves against the greater than component, which is gonna tell us if it is greater or equal than a certain number that we decide. So we're gonna use a slider for that. And we want to have this as our input in B, and we want the length of the curves to be our input in A. So now we should have as an output true-false structure. And yes, so the first one, the first curve, which is the very, very short one, shows up as false. And actually, it might be a good idea to have this all flattened so we don't end up with empty lists. And we go and use curl pattern to do that. We have our pattern ready. And then we use the original curves as a list. So now we have all the original intersection curves, but the first one. Okay, so now we want to divide the closed planar curves and the open planar curves. So we want to do that because at some point, especially for the closed curves, we will need to control the seam. We want the seams to line up on all closed curves. There is a component, a curve component, that will look for closed and open curves. It will return a true-false pattern, and this is what we're going to use. So these are the curves that we want to check. There we go. And now we have all the closed ones. At some point, we will also need to have the open ones, and it's going to be just a matter of inverting the pattern. And so we have the list, and we want to Yes, we want to line them up with the YZ plane intersection.
What about showing the endpoints for these closed curves?
I
Just
feel this is the
yeah, it's just as
yeah.
a reference. You see that? So it's somewhere here and here. We would like to have the endpoints to line up nicely, maybe along the YZ plane, so that
Yeah.
you get something like this. And imagine that would be the starting point for laying the stones down. So you said we need a vector YZ plane. So we want to go into the intersection and get this guy here, curve plane intersection, what we're looking for. Okay, so we have lists with 2 points. We just need one of them for each curve. We just need to have a list item connected, not exactly to the points, because the scene will look into parameters. And we want to look for the item 1. Okay, so this is what it will do. It will look into all the item number 1 from all the lists. So we don't need the list to be divided. We just want one list with many values so that we can match them with the curves, which is one list with many values. All right, so easy way, flatten. There we go. And that's what this will make it consistent with the list of curves that we have. So now we have a list of curves we want to adjust the seam of, and we have one list of values that are parameters. Okay, we don't really see much here, right? Because the only way to get the points is just endpoints. And there we go. Now we have them all nicely lined up.
Okay, so maybe we want to work on the open curves now, which actually don't need much handling, just to be divided from the open ones. So we can do that by copying the component that we used to extract the closed curves and inverting the pattern. So we can right-click on the pattern and go invert. And this way we get the open curves instead. So we have both closed with seam adjusted and open curves now.
Let me get rid of this big panel here. And the endpoints, which we also use as a proof of concept that the seam was working as expected.
Okay, so now we want to get the length of both those classes of curves. So let's call them like that. So both open and closed curves, because we want to estimate how many stones will fit in each curve by dividing the length based on the size of the stones. So we want to control that with a slider. And we also want to keep just the integer part of the division, because what we care about is the number of segments, so the number of stones. And we want to fit that into a divide curve component. So right now we're setting up the slider with some reasonable values. So
very optimistic 5, which would be a very large stone.
Yes,
but,
yes.
Yeah, but in our example, I think we were, using something like 1.5.
Yes, so now we get an expression component where we can write the integer division part, and we can feed the length. So the length is going to be x, and the value we divide for is going to be y.
So let's write the expression. Now, you correctly stated that we need the integer part. So in case you don't remember how to type that, you have a list of the functions over here. and you will see that you can scroll down, and this is how you write the integers. So it's capital INT, and then it's the value is going to be in brackets and close brackets. And this is giving you a feedback in whether there are syntax errors or not. So
It seems we're good.
Okay. Let's just feed the panel with the result. You see, we're getting the numbers. This time we will divide by number. Remember, we did a division at the beginning, which was based on distance. Curves are going to be both open and closed curves. Okay, let's just provide the list with the same order you're giving it here. Otherwise, you get divisions that are not, working in the proper way.
All right, so you know what, to avoid any confusion by, having to remember which list we plugged in first and maybe we get them mixed up, should we use a merge component to make sure we're working with the same data all the time? So that is
Sure.
kind of a fail-proof method, I
Yeah,
think.
so you know that the closed curves are D1, the open curves are D2, and you see that this will add a new entry point anytime you're adding something. So we're just, it looks like it's redundant, but it's not at all. Okay, so we know that which one is which.
Yes,
and so
to avoid confusion down the road.
Absolutely, you're right.
Yes.
Wow, I can
nice.
already see something good is popping up here.
All that work paid off.
Yeah, you know what? Shall we just get rid of lots of visualization planes and stuff like that? If we need the curves to be seen, maybe we can preview them here, just in case we need them. Okay.
So maybe we want to have an even better visualization of the stones placed on these points. So maybe we want to have some placeholder spheres or some kind of geometry.
Yeah. I think I would go for the spheres.
The spheres seem like
So yes, it's just just to prove what we're doing, and all the spheres are going to be placed on the points, and the radius is going to be half this value. Okay, so you don't want to really make the whole, get math component division. There's a quick way of doing this. Right click on R, expression, variable is always going to be X, and feed this value, because we're talking about radius, and then place the origin, the base point for the spheres in all the points. There you go. Not bad, huh?
Not bad at all.
No. And now the fun part is that you can change the size of the stone. You can change the distance between the curves. This is where this is starting to pay off, because as you change this, you see, everything will start changing accordingly. And so all this trial and error that you would be doing in Rhino, in direct modeling, it's something that you can do on the fly here. Like, now they're just too close to each other, I think. But you know what? It's really time maybe to bake these spheres and have a quick check in Rhino with all the pieces that are missing, because we are getting an idea here, but it's not really helping us much. Let's add the bits and pieces. Well, now the ring is starting to
look like something. Yes,
exactly. So you know what, let's look at artistic view. Now if there's one thing that I find really tricky in jewelry design, and I tell you, it's something that even after years is hard for me to sort of like figure out, is the zooming. Now, the zooming is really something you have to be careful about, because we have the ability to really go into the most minute detail of our objects. But while this is an advantage on one side, it can be a really major drawback, because you end up not really getting the right proportions of what you're working with. And I find something very useful, and I'm not sure if this is a feature that is so much used, is the ability to get into the one-to-one scale. Now, you want to calibrate that the view, because this goes according to the screen size that you have. But if you right click here, you are prompted with something that will, you will have to measure with a caliper or a centimeter, whatever that will be. Like this bar for me would be like 127 something. You have to physically place the ruler on top of this bar and adjust this number accordingly. But once you're done with this and you go back to the command and you go zoom 1-to-1, now you're seeing the object as it would be in real life. And this is so good, because you see how the lineup of the stone is nicely organized. I think we did a good job here. What do you think?
It is super tricky to get a correct idea of the proportions without a tool such as this. So this is really valuable, I feel. It looks really good.
I think so. I think so. We have enough spacing so that you can really read the fact that the stones are laid out. Now we have spheres here, but it's already telling us that this is a good organized layout,
Yes.
circular organization of the stones. I think it's
exactly
it
looks a lot like what we pictured when we were thinking about it.
Okay. Okay. And if the customer will ask for more space between one line and the one circle of stones and the other one, is going to be really easy. It's just we just go back to the definition and increase that space in the division, and everything will come up right away without having to redo the whole thing. And we will be able to apply this also to other circumstances, other objects, not only this ring. So I think that taking a bit of our time in doing the definition will pay off really well.
I agree with this philosophy.
So what do you think? What should we think about in the next episode? Is there something you think we can build on top of this?
All right, so a couple of things need a little bit more work. I feel like some of the stones that are very, very close to the edge of the surface are going to be
you mean like this one?
Yes, there's I see four actually from this, roughly four from this this visualization. So yes, those four. I feel like they are a little bit too close to the border, and that we can intervene on that through Grasshopper. So when we change the size of the stones and all of that jazz, we can avoid removing them manually as we did. So that's a little bit more work on the definition, but
so a way to
call
the points that are closer than a certain value.
Yes, I would do something
with respect to the edge of the surface.
Absolutely.
That would be the strategy. Okay, for the next refinement of the definition. Okay.
Yes, and maybe this time we can play with stones. So there's a little bit more orienting to do to have the stones facing the right direction. But it's not much work really. We're off to a great start. We're actually pretty much finished at this point. It just needs some adjustments, and then maybe we can have a rendered version of this model with the prongs and all, just to visualize better how it's going to look in real life. These are the things that I feel we will work on the next
Okay,
episode.
so we will pick up starting with the definitions, with the definition we just finished, and polish a little bit of that,
Yes.
and add the placement of the real stones. So they're orienting the stones on the surface and centering them on the point that we have defined, like centers of the spheres. Okay, we have some work to do, but it's going to be for the next time.